Right. I'd like to do a revision on complex numbers and vectors for you guys. This is actually not part of my module, but is one of the very important mathematical tools that we use in control engineering. And in the past, I found people struggling a lot with vector numbers, and it really affects their understanding of control subjects. So it's actually quite essential, although it is, again, it's not part of my module, but it's essential that you have a better understanding on what to do with complex numbers and how to do them, basically. And sometimes people use calculators, but it's much better to understand. So even when you use calculators, some calculators actually do complex number for you, but it's important that you know what you're doing with your calculators. So basically, complex numbers come with two forms. One is known as rectangular form, which is equation number 1. So there are two parts of the complex number. There's a real part, there's the imaginary part. Now in mathematics, people use I to represent the imaginary part, but in engineering, we use J. Okay, so it's A plus JB, that's the vector numbers in rectangular form. The complex numbers can also be represented in the polar form, which is the magnitude and phase angle. So we have m times e to the power of j theta. So the first part is the magnitude. The second part indicates the phase angle of that number. Now sometimes we don't use e, we use m for the magnitude. We just use this sort of color shape to represent the angle. Okay, so I use this form a lot in equation number 3. Okay, graphically, if you look at the graph, the S-plane or complex plane on the right, this is the real axis. So x-axis is my real axis. The y-axis is the imaginary axis. So if you look at equation 1, real part is a, so it's here. Imaginary part is JB. Okay, so B is here. So if you draw a level line here, you draw a vertical line there, this line indicates this complex number y. So this one has, or you can actually go other way around. If you project y onto the real axis, you get A. If you project the y onto the imaginary axis, you get B. M is the distance between the point of origin to the end of the vector or the complex number. Theta is the angle between this red line and the real axis or the positive part of the real axis. Okay, sometimes we use an arrow, or it's useful to always use an arrow actually, pointing away from the point of origin just to show the direction of the vector. So the end, this is start, this is the end. This length is m, this is theta. And of course, we have a bit of trick here. So they are interchangeable between the two forms, between the rectangular form and a polar form. Because if you look at this triangle here, this is a right angle triangle. This is A, this is B. So A squared plus B squared equals to M squared. Therefore, M equals to square root A squared plus B squared. Angle, this angle equals to this opposite to the angle, so that's B. B over A, that gives me a tangent theta. Therefore, theta equals to arctangent B over A. So that's how we convert from rectangular form to polar form. Or you can actually go from polar form to rectangular form. If I know m and theta, then of course this is this is m, this is theta, this value equals to sine, so b equals to sine theta times m. This is length of a, so a equals to m times cosine theta. So they are interchangeable between the two forms, but just that sometimes it's easier to use rectangular form, sometimes it's easier to use polar form. So you need to know, really get yourself really familiar with this kind of conversion at the bottom of this slide. So this is from rectangular form to polar form. This is from polar form to rectangular form. You need, when you see a vector, you need to be able to visualize it in the complex plane. So it makes life a lot easier for us. Okay. Now, rectangular forms are good when we try to add or subtract complex numbers. So if I, for example, I have two numbers here, just some random a plus jb, c plus jd. If I try to add the two together, what you do is add the real part to real part, imaginary part to imaginary part. If you want to do a subtract, you subtract the real part, you subtract imaginary part. Okay, real part, imaginary part, they don't get mixed up. And this is real, this is imaginary. You can't add real to imaginary. No, it doesn't work. But when we do a multiply or divide, it's best done in the polar form. So you need to really convert whatever. If they are not already in the polar form, you need to convert them into polar form. Because then, if I multiply two complex numbers in polar form, all I need to do is actually I'm going to multiply the magnitude. So this magnitude is m. This magnitude is n. So I multiply m to n. That's give you an overall magnitude. But for the angle, we don't multiply, we add. Okay? You add them together, so you get theta plus phi. When you do division between two complex numbers, you divide the magnitude, so m divided by n, but you subtract. Okay? You subtract the angles. So this becomes theta minus phi. So remember this. Rectangular form for addition and subtraction. Add real part to real part, imaginary part to imaginary part. Multiplication or division, you use polar form. You multiply magnitude or divide magnitude, and then you add face angles for multiplying, but you minus face angles when you divide. I've got some few examples here. Okay, so I have two complex numbers. One is x equals to 3 plus 4, y equals to 8 with an angle of 30. So that's my first question. Okay. I want to, for example, if I want to add the two together, this is what I need to do. I need to convert this equation, this, into rectangular form. Okay, so it will be 3, so 3 plus 4 plus 6.93 plus j4. Then you add real part to real part, imaginary part to imaginary part. So that's my equation number 3. Equation number 3 is basically trying to do the addition of the two numbers. If I want to subtract, again, you subtract this number to this number by this number. But this needs to be in the rectangular form. So you convert that into rectangular form, which is the equation number 4. So this should be minus. So y, x minus y equals to 3 plus j4 minus 6.93 plus j4. That will give me minus 3.93. That's real part add to real part, or real part minus real part. Imaginary part is j4 for the first number, but the second number is also J4, so J4 minus J4, therefore the imaginary part disappears. Okay, if I want to multiply the two numbers in equation 1a and equation 1b, now this is okay, y is okay, x is not, so I need to convert that x into the standard form, sorry, into the polar form, which is 5 angle of 53. Okay, so converting, last time when we tried to do addition or subtraction, we need to convert this polar form into the rectangular form. Now, because I want to do multiplications, I need to convert this into the polar form. Now, x times y equals to this times that. So that's 5 times 8. That gives me 40. Angle 53 add to angle 30. That gives me 93. That should be add. Okay. If I want to divide these two numbers, then it's 5 angle 53 divided by 8 angle 30. So it's magnitude divided by magnitude, angle minus angle. So 5 over 8 give me 0.4. 53 degrees minus 30 degrees, that gives me 23 degrees. So there's a slight correction here. This is plus. Okay, this is minus. So the example that just shows, it's easier. It's easier to convert between them, but then there are forms that you want to do. Add. So if you get a number in rectangular shape, and then you need to multiplication, you need to do the multiplication, then you need to convert that into polar form. If you have a complex number in the polar form, but you need to do addition or subtraction, then you convert this into rectangular form. So it's easier. Add these two together or subtract these two is easy. Multiply these two or divide these two is easy. See? So although they are same number, they represent the same, exact same thing. This x is the same as this x. This y is the same as this y. Just that they're different in forms, and they make life easier for the calculations. We also represent them in complex plan or in the S plan, as I mentioned earlier, and in different quadrants. They actually have different representations for the real part and imaginary part, and for their face angle. So in the first quadrant, the angle will be between, the maximum angle will be between 0 and 90 degrees. Okay, the angle will be between 0 and 90 degrees. In the rectangular form, both real and imaginary part will be positive. Okay, A will be positive, B will be positive. In the second quadrant, it's between 90 degrees and 180 degrees. Now this time, because the real part is negative, so you can see there, the real part in the rectangular part, real part will be negative, imaginary part will remain positive. In the third quadrant, now this time we can look at the angle from the negative side. So you have an angle between minus 90 degrees to minus 180 degrees. This time, the real part and imaginary part are both negative. Finally, in the fourth quadrant, the angle is between 0 to minus 90 degrees. In the rectangular form, real part is positive, imaginary part is negative. So it's all clear. The reason I want to show this is that sometimes people rely on the calculators. Now, it's fine when you do some conversions, for example, from polar form to rectangular form. But when you work other way around, sometimes it can be a bit tricky. For example, if you compare this case and that case. Now this case is opposite. One is the second, one is in the third. This is negative real, positive imaginary. This is opposite, positive real, negative imaginary. But if you do a B over A, the imaginary over real part, imaginary part over real part, you get tangent theta. But tangent will always be a negative. But which part of the negative? Shall we get an angle between 0 to minus 90 degrees, or you get an angle between 90 and 180 degrees? You have to make that judgment. The calculators are not that clever. They don't know what you got in mind. If you give them a negative number, most likely it will give you this angle, an angle between 0 and minus 90 degrees. It doesn't know anything about whether you had a positive or negative for the real part. By the same argument, if you do a imaginary part divided by real part for this, when the number is in the first quadrant, you get a positive. If you do a real imaginary part divided by real part in this for this number, you also get a positive. Well, how does it calculate now? It's a positive number. You try to do an arctangent positive number, you will get angle between 0 and 90 degrees. You won't get that. A lot of mistakes are made like that because people don't distinguish between this and that, or this and that. That's something that calculators can't do. So you have to make sure that you know what you are working on. So these are the 4 quadrants. Taking the 4 quadrants, but we can also look at four very extreme cases as well. So that means the vectors or the complex number sits on the axes. So in the first quadrant, real positive number, that's a number pointing towards the real part of the positive part of the real axis. So the angle will be 0 because it's in line, in parallel with the positive part of the real axis. So angle will be 0. The magnitude will be A. If you have a complex number like that, which has only the imaginary part or positive imaginary part, then this number is JB. There's no real parts. And JB is actually 90 degrees. See, this is the angle there. So you have a magnitude of B, the angle of 90 degrees. If you have a number that's a negative real, so on the complex plane, it's actually pointing towards the negative side of real axis. So you have an angle of 180 degrees. So you can have a positive 180 degrees. We can also have a negative 180 degrees. Both the same because they end up with the same number. Okay, so the magnitude here is A. The angle is 180 or minus 180. So you have to be clear. This A, the first A, y equals to A, is in the rectangular form. Second is in the polar form. Okay, polar form comes with the angle, even though the angle may be 0. Okay, this only have a real part, imaginary part. That's in the rectangular form. This is in the polar form. Polar form comes with magnitude and 90 degrees. And the same for here. Minus A is rectangular form, but A angle of 180 degrees or minus 100 degrees, that's the same number in the polar form. And again, that's the one you can actually derive from there. Minus JB is B, magnitude is B, angle is minus 90, sorry. So from there to there, that's minus 90 degrees. But magnitude, the length of that number, is B, so magnitude is B. So minus JB is the same as B angle minus 90 degrees. But sometimes people get confused about these things like that. So A is the same as A angle 0, because if that's a positive number. Minus A, if it's a negative number, it's the same as A angle 180 degrees. JB is the same as B 90 degrees minus JB is the same as B minus 90 degrees. So these are special cases, but they sometimes come up in your questions. Also, it's useful if we know how to add or subtract graphically. Okay, because it's part of the process that we can do. If we can do them numerically, but we can also do them graphically. So over here, what I have is X in that red, so pointing towards this way, and I have a Y pointing there. If I want to find X plus Y graphically, there are two ways you can do it. Either you can draw a parallel line to the Y over here. Or you just say, right, I'm not going to draw any parallel line. And you can draw a parallel line here to the X. Then what's in the diagonal of that shape is your answer. So that. Okay, just let me repeat. You draw a parallel line to Y, and you draw a parallel line to X. So there's a parallel line there, there's a parallel line. What's in the diagonal is your M value. M, and this angle is the face angle of that complex number. Okay. The second method is that if I have first number X, I know that's X. At end of the X, I just draw Y, or a line parallel to the Y, pointing towards down, see? So I'm adding Y. This Y, it's like I move the Y to here. So it's X plus Y. At end of Y arrow, and then I'm going to draw a straight line from the point of origin to the end of Y. That's my new complex number. So I'm going to draw that from there to there. So X, draw Y to add Y to the end of X. Now we carry arrows. At end of Y, that's where the arrow is pointing to. So I'm going to draw a line between point of origin towards end of Y. That's my X plus Y. And that's my angle there. Okay, two approaches. Either you draw a parallel line or you just add to another. Subtract is slightly more complex, but once you work it out, it's not that difficult. So consider X minus Y. This is my X, this is my Y. X minus Y is the same as X plus negative Y. Negative Y is opposite to Y graphically. So I'm going to draw a line there opposite to this Y, and then I'm going to add X to the negative Y. Okay, negative Y, so I'm using the previous method. So add negative Y to X, this is X. So I'm going to start draw the negative Y from the end of X towards there, that's the same direction. And then I'm going to draw a line between the point of origin towards the end of negative Y. That's my M. Okay, so that's first approach. You have to find the negative Y first. Now my second approach is a bit easier. What I do is I have two numbers here. I have to do an X minus Y. So I'm going to draw a line from starting from the end of the second number, that's y, that's negative minus y, okay, from second number towards the end of the first number. Okay, so x minus y is second number, start from here, end up at end of second number. So that's my m. That length is my m. The angle between this line and another line in parallel with the real axis is my angle of that number. Okay, so this is theta, but this line, dotted line or dashed line here is in parallel with the real axis. So if you draw a line there, the length is m, okay, end to end of x and y, but pointing towards the first number. That length is m. This angle in parallel with to the line in parallel with the real axis is your phase angle of that complex number. Okay, so that's enough of an introduction, and I've set some practice questions for you to do. Thank you.